and I will take each of the quantities that are listed in the final row of my rice table, and I will create this algebraic equation so we can solve for x. So what goes in the numerator would be x times x. What goes in the denominator would be the quantity 4.18 minus 2x, which is squared, and I set that equal to the value of Kp, which is 81. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 7.5 to 7.8. As you can see on this slide, these topics fall under Unit 7 in the AP Chemistry curriculum, Equilibrium. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 7.5, magnitude of the equilibrium constant. Here is an essential knowledge statement from the AP Chemistry course and exam description. Some equilibrium reactions have very large K values and proceed essentially to completion. Others have very small K values and barely proceed at all. Now let's move on to the practice for topic 7.5. This is question 1. In question 1, it says that CH3OH reacts with HCl according to the following equation. And you will notice that the equilibrium constant is listed as 4.7 times 10 to the third. And when you see a very large value of K, so typically that would be on the order of 1,000 or greater, it means that the reaction essentially goes to completion from left to right. So that's an important point to answer question 1. The question goes on to say that a 0.25 mole sample of CH3OH and a 0.75 mole sample of HCl are introduced into a rigid previously evacuated reaction vessel and allowed to reach equilibrium at 400 Kelvin. Which of the following is true at equilibrium? And we can see among the 4 choices that we have to compare the relative concentrations of CH3OH, HCl, and CH3Cl. Now, this is a strategy that we will use in question 1, which is a strategy that I had introduced in my previous lesson, which also involved concepts of equilibrium, and that is when you need to keep track of the amounts of the reactants and products during the course of a chemical reaction as the system moves toward equilibrium, creating a so-called rice table is a good strategy. And you can see that the word rice is an acronym for reaction, initial, change, and equilibrium. So the first thing that I will do in this rice table is to fill in the initial row of the rice table with the amounts that we have before the reaction takes place. 0.25 mole of CH3OH, 0.75 mole of HCl, and then that's it. They did not add any of the products to the reaction vessel at the very beginning, so I will fill in those quantities as 0. Now, with respect to the change row of the rice table, first, I will fill in the change row of the rice table in terms of x. And remember that the magnitude of the changes, whether that's minus or plus, should be in proportion to the coefficients in the balanced chemical equation. But you will notice that all of the coefficients are 1 in this balanced equation. So then the change will either be minus x for each of the reactants or plus X for each of the products. Again, that's because all of the coefficients are 1. That's why it's X as opposed to 2X or 3X or things like that. So at equilibrium, we have, in terms of moles, 0.25 minus X for the reactant CH3OH. We have 0.75 minus X in terms of moles for the other reactant HCl. And then in terms of the moles of each of the products at equilibrium, that would be X and X. Now I will briefly bring up the topic of limiting reactant, which is something I had mentioned back in an earlier lesson in Unit 4. It was topic 4.5 involving stoichiometry. So here we have to identify the limiting reactant. So based on that 1-to-1 mole ratio, the fact that 0.25 is less than 0.75, we can see that if this reaction does go essentially to completion, the smaller number of moles in this case, for the CH3OH, that will be consumed completely, essentially completely, and there will be some extra or leftover HCl when this system reaches equilibrium. So the change row of the Rice table will now be in terms of minus 0.25 for the reactants or plus 0.25 for each of the products. And so at equilibrium, 0.25 minus 0.25 means that even though it probably will be a very small number, it will be approximately 0, the amount of moles of CH3OH. That will be the smallest of all 4 substances present in terms of quantities in the reaction vessel at equilibrium. 0.75 minus 0.25 will give us 0.5 moles of HCl present in the reaction vessel at equilibrium. And then for each of the products, it would be 0.25 moles. At this point, now we can go ahead and make that comparison. So with our Rice table complete, let's go ahead and eliminate choices C and D. And the reason why we can eliminate choices C and D is because it says that HCl is the smallest concentration, and that is not true. The substance with the smallest or the lowest concentration in equilibrium would be this reactant CH3OH. So the correct answer is either choice A or choice B. Now, the substance that has the highest concentration, looking at our Rice table, would be HCl. And that's because 0.5 obviously is larger than 0.25. So we can now say with confidence, with our Rice table, that the correct answer to question 1 is choice B. CH3OH should have the lowest concentration, and HCl should have the highest concentration when the system reaches equilibrium. All right, well, hopefully that explanation with that Rice table makes sense. Now, let's go ahead and take a look at question 2. In question 2, it says the following. The ionization of aqueous HF in water is represented by the equation above. In a solution of 0.10 molar aqueous HF at equilibrium, is the concentration of F-, the fluoride ion, less than, greater than, or equal to the concentration of HF? Justify your answer. So just like we saw in question 1, we need to consider the magnitude of the equilibrium constant K. But unlike question 1, where there was a very large value of K, here in question 2, we see a very small value of K. So the value of Ka for this reaction is 6.8 times 10 to the negative 4. And so the reverse reaction from right to left essentially goes to completion, and we would expect the products to have a smaller concentration than the reactants, since this reaction essentially goes to completion from right to left. So that's how we will answer question 2 with our justification. Is the concentration of F- less than, greater than, or equal to the concentration of HF? And the answer is less than. So here is the justification. The value of Ka, or the equilibrium constant for this reaction, is less than 1, which means that the reactants are favored at equilibrium. Therefore, the concentration of F- should be less than the concentration of HF at equilibrium. Now, let's move on to question 3. And just like we saw in question 1, I can see a Rice table that's already been started for us. So we created a Rice table in question 1, and that will be a handy strategy in question 3. Also, similar to question 1, we have a very large value for the equilibrium constant K. And then also in a similar fashion to question 1, we should consider the concept of a limiting reactant as we are filling in this rice table. So let's consider the information presented in question 3. It says samples of Q2 and X2 are introduced into a previously evacuated rigid container. A chemical reaction occurs according to the equation shown above until equilibrium is reached at 700 Kelvin. The initial concentrations of Q2 and X2 in the reaction vessel before any reaction occurs are listed in the table below. Part A of question 3 says, considering the value of Kc, fill in the missing information in the table in order to determine the concentrations of all 3 substances present in the reaction vessel when the system reaches equilibrium at 700 Kelvin. So again, as I had mentioned, the value of K in this question, just like we saw in question 1, is very large, 8.0 times 10 to the 11. So when you see a very large value of K, it means that the reaction essentially goes to completion from left to right. Now, what I will do is fill in the change row of the rice table in terms of X. So again, remember that the magnitude of the changes for reactants and products should be proportional to the coefficients in the balanced chemical equation. And with coefficients of 1, 3, and 2, then the magnitude of changes in terms of X will be X, 3X, and 2X. So as I fill in the change row of the rice table, it's going to be minus X for Q2 in terms of the change in that reactant. It will be minus 3X in terms of the change for the other reactant because of that coefficient of 3. And then to produce the product, QX3, it has a coefficient of 2, so that will be plus 2X. Now, the next thing that we need to consider with respect to the reactants is which reactant, Q2 or X2, will be the limiting reactant. Notice that we have a 1:3 ratio of Q2 and X2 in the balanced chemical equation. However, we do not have a 1:3 ratio in terms of those concentrations. So the numbers that I see are 1.2 and 2.4. Now, they could represent either the moles or the molarity. They still would be in a ratio of 1:3 if each of these reactants was consumed completely, but that's not the case. One of these substances will be the limiting reactant, which would be consumed completely for this very large value of K, that the reaction is essentially going to go to completion from left to right, but then the other reactant will be left over. Now, at first glance, you might be looking at 1.2 and 2.4 and thinking that because 1.2 is the smaller number, you might be thinking that that makes Q2 the limiting reactant. But watch what happens when I do a little bit of math to see how this is going to work. 1.2, assuming we had a number of moles, 1.2 moles times 3 would be 3.6 moles. So if we replace molarity with moles, we can still make this comparison. Do I have 3.6 for my molarity or my number of moles for the other reactant? And the answer is no, I don't have enough X2 available to react with all of the Q2. So that makes X2 the limiting reactant. So X2 is the limiting reactant because 3.6 mole is needed, but only 2.4 mole is available if I assume I have a 1 liter container. So why is that important to identify the limiting reactant? It's because now I can fill in the rice table based on that change in the amount of the limiting reactant. So instead of writing minus X, minus 3X, and plus 2X, I will focus on my limiting reactant, which, if it is consumed completely, that will decrease by 2.4. And since the number X is 1/3 of the number 3X, because of that 1:3 ratio, what is 1/3 of 2.4? So 1/3 of 2.4 will be the change for Q2. That's why I'm putting minus 0.8 in the change row for the other reactant. Again, you can see that the change is proportional to the coefficients. And then 0.8 times 2 is 1.6. So for the product, that should be twice as much in terms of the change compared to Q2. So 0.8 times 2 is 1.6. So I have now filled in the change row of the rice table, having considered that X2 is the identity of the limiting reactant in this experiment. So my change is minus 0.8, minus 2.4, and 1.6. So obviously 0 plus 1.6 is 1.6. 2.4 minus 2.4, that means that I have essentially a very, very small number for my amount or my concentration of X2 at equilibrium. And then 1.2 minus 0.8 is 0.4. So now what you're looking at in that final row of our rice table is the answer to part A of question 3. Remember that it said, considering the value of K, which we did, K is a very large value, so the reaction essentially goes to completion. Fill in the missing information in the table in order to determine the concentrations of all three substances present in the reaction vessel when the system reaches equilibrium at 700 Kelvin. So that would be, at equilibrium, the concentration of Q2 is 0.40 molar. The concentration of QX3 is 1.6 molar, and the concentration of X2 at equilibrium is a very small number, so approximately 0. This is a good transition to part B of question 3. So part B says the following. At equilibrium, the concentration of X2 in the reaction vessel is a very small value, but not exactly equal to 0. Calculate the concentration of X2 in the reaction vessel at equilibrium. So what I will do is write the equilibrium constant expression, Kc, and that would be products over reactants. So that would be Qx3 on the top, Q2 and X2 on the bottom. So my equilibrium constant expression looks like this. And you can see I'm using hard brackets because this is a Kc. If it were a Kp, I would have used capital P for partial pressure. So concentration of Qx3 squared divided by the product of the following. Concentration of Q2 times concentration of X2 cubed. Now, the next thing that I will do is set up an algebraic equation, and I will plug in everything that I know except for the concentration of X2. And then I will solve for the concentration of X2. And my prediction is that the value for the concentration of X2 will in fact be a very small number. All right, so I have set up the concentration of Qx3 from the rice table. That would be 1.6, and the concentration of Q2 in the rice table is 0.4, and the concentration of X2 is unknown, but it's going to be a very small number. I set this expression equal to the Kc, which is 8.0 times 10 to the 11. Now I just need to do the algebra to solve for the concentration of X2. So the next step in my process will be to rearrange this equation so I can get the concentration of X2 on one side of the equation. So you can see what I've written is 1.6 squared divided by 0.4, but then also divided by 8.0 times 10 to the 11, and I set that equal to the concentration of X2 cubed. So on my calculator, when I did that math, 1.6 squared divided by 0.4 divided by 8 times 10 to the 11, I get 8 times 10 to the negative 12. Now, this is not my answer because I still have to take the cube root of this value. So the cube root of 8 times 10 to the negative 12 will give me the concentration of X2 at equilibrium. What I am expecting is a very small number. So when I do this math, I get the answer to part B of question 3. The concentration of X2 in the reaction vessel at equilibrium is in fact a very small value. 2.0 times 10 to the negative 4 molar, that is the answer to part B of question 3. So to answer question 3, we had a rice table. We had to consider the large value of K, means that the reaction essentially goes to completion, and we had to consider the concept of the fact that limiting reactants were available, and that was X2 was identified as the limiting reactant. And then we finally did a little bit of algebra, simply plugging in all of the values that we knew, and then solved for the one value that we didn't know, which was the concentration of X2 at equilibrium. Well, hopefully all of that makes sense to you. Now it is time to move on to the review for topic 7.6, properties of the equilibrium constant. And here are some essential knowledge statements from the AP Chemistry course and exam description. When a reaction is reversed, the equilibrium constant K for the reversed reaction is equal to the reciprocal of the original K. When the stoichiometric coefficients of a reaction are multiplied by a factor n, the equilibrium constant K for the modified equation is equal to the original K raised to the power n. When reactions are added together, the equilibrium constant K of the resulting overall reaction is the product of the individual K values for the reactions that were added together. And since expressions for K, equilibrium constant, and Q, reaction quotient, have identical mathematical forms, all valid algebraic manipulations of K also apply to Q. Now it's time to move on to the practice for topic 7.6. This is question 4. In question 4, it says, based on the information above, what is the value of the equilibrium constant K for the reaction represented below? So both in question 4 and in question 5 of this packet, our job is to consider what changes were made to a particular balanced chemical equation, and then how will those changes affect the numerical value of K. So as we consider the original equation, which has coefficients of 1/2, 1/2, and 1 from left to right, and then this modified equation, which has coefficients of 2, 1, and 1, we can see that most likely the coefficients were multiplied by 2. But you also notice that the HBr shows up on the right in the original equation, and now the HBr shows up on the left in the modified equation. So the answer, what changes were made to the original equation, is the following. The original equation was reversed and each of the coefficients were multiplied by 2. So going back to the essential knowledge statements for topic 7.6, when a reaction is reversed, the K for the reversed equation is equal to the reciprocal of the original K. So that would mean that if I just reversed the equation, then I would write 1 over, or 1 divided by, 1 times 10 to the 2, the original value of K. But there's also that issue of multiplying each of the coefficients by 2. So again, in topic 7.6, it says that when the stoichiometric coefficients of a reaction are multiplied by a factor n, the K for the modified equation is equal to the original K raised to the power n. So not only do I need to take the original K and write the reciprocal, I also need to raise it to the second power based on multiplying each of the coefficients by 2. So when I pick up my calculator and I do 1 divided by 1 times 10 to the 2, and then I square that value, this is what I get. And the correct answer to question 4 is choice A, 1 times 10 to the negative 4. So we will also see some manipulations to balanced chemical equations in question 5. Let's go ahead and take a look at question 5. So question 5 says the following. The chemical equations listed in the table above have been modified and added together to produce a third equation as shown in the table below. Determine the value of the equilibrium constant Kp at 300 Kelvin for each equation listed in the table above. So I'll start with the first equation listed in the table above. So what change was made to that particular equation? It looks like the coefficients were not affected, but simply that the equation was reversed. Again, remember that when a reaction is reversed, K for the reversed equation is equal to the reciprocal of the original K. So 1 divided by the quantity 5 times 10 to the negative 2, that will give me the new version of K. So the new version of K mathematically is equal to 20 when I do that math. Now, the next modified equation would be this particular one, and it looks like the change that was made is that each of the coefficients in the original equation was multiplied by 2. Again, that will mean that the new value of K will be the original value of K raised to that power. So if I take the original K and I raise it to the second power, or I square it, 4 times 10 to the negative 3 squared will give me the new value of k for this modified equation. And when I do that math, I get 1.6 times 10 to the negative 5. Now, since these two equations, these modified equations in the bottom table, have been added together, when reactions are added together, the k of the resulting overall equation is the product. So we have to multiply the individual k values together to get the new value of k. So I'm just going to cross off the 2d and the 2dx just to verify that when these two equations are added together, we get 2ax plus x2 producing 2ax2. So yes, that works. And now what is my new value of k for the overall equation? It would be the product of 20 times 1.6 times 10 to the negative 5. And so when I do that math, I get 3.2 times 10 to the negative 4. So we're just simply showcasing the different ways in which a chemical equation can be modified, and then how the equilibrium constant for that modified equation is related to the original value of k. All right, well, hopefully the answers to questions 4 and 5 make sense. Now it's time to move on to the review for topic 7.7, calculating equilibrium concentrations. Here are some essential knowledge statements from the AP Chemistry course and exam description. The concentrations or partial pressures of species at equilibrium can be predicted given the balanced reaction, initial concentrations, and the appropriate value of K. When the reaction quotient Q is less than the equilibrium constant K, the reaction will proceed with a net consumption of reactants and generation of products. In other words, a net conversion from left to right. On the other hand, when the numerical value of the reaction quotient Q is greater than the equilibrium constant K, the reaction will proceed with a net consumption of products and a generation of reactants. In other words, a net conversion from right to left. And if the reaction quotient Q is equal to the equilibrium constant K, then the system is at dynamic equilibrium. Both the forward and reverse reactions proceed at the same rate, and the proportion of reactants and products remains constant. Now let's move on to the practice for topic 7.7. This is question 6. In question 6, it says that hydrogen gas and iodine gas react to form hydrogen iodide at 458 degrees Celsius according to the equation above. Equimolar amounts, in other words, same number of moles, equimolar amounts of hydrogen gas and iodine gas are placed in a previously evacuated 4-liter rigid reaction vessel where they react at constant temperature at 458 degrees Celsius according to the equation above. After the system had reached equilibrium, it was determined that the concentration of HI in the reaction vessel was equal to 1.40 molar. So part A of question 6 says, calculate the concentration of hydrogen present in the reaction vessel when the system had reached equilibrium. Now, technically, you could just simply set up an algebraic equation using the equilibrium constant expression for this reaction to answer part A. You don't necessarily need to create a rice table to answer part A of question 6. But I'm going to go ahead and create a rice table now. And the reason why is because this will definitely help us when we get to part B of this question. So the value of creating a rice table now is that I can just keep track of everything from the initial set of conditions, the change, and then what's present in the reaction vessel when the system had reached equilibrium. So the first thing I will do is fill in as much as I can the initial quantities. Well, the problem is that we don't know the initial number of moles or the initial concentration for hydrogen and iodine. All we know is that it's the same number of moles. So I will, at this point, fill in my rice table with simply capital N as a variable. The number of moles of hydrogen is unknown, but it's the same as the number of moles of iodine initially. And they did not add any hydrogen iodide initially, so that quantity is 0. Now, with respect to the change, remember that the magnitude of the changes for the reactants and products in my change row of my rice table should be proportional to the coefficients in the balanced chemical equation. So we can see that this balanced equation has coefficients of 1, 1, and 2. So therefore, the magnitude of the changes would be x, x, and 2x. So minus x for the hydrogen, minus x for the iodine, and then plus 2x for the hydrogen iodide. Now, at equilibrium, we are told that when the system has reached equilibrium, the concentration of HI in the reaction vessel is 1.40 molar. Now I will set up an equation using the equilibrium constant expression for this reaction and then do some algebra to solve for the concentration of hydrogen present in the reaction vessel when the system had reached equilibrium. So there is the equilibrium constant expression, Kc. It's going to be concentration of HI squared divided by the product of the concentrations of hydrogen and iodine. And at this point, the concentration of HI at equilibrium is known, whereas the concentrations of hydrogen and iodine at equilibrium are unknown. So that's why I have to solve for the concentrations of hydrogen and iodine at equilibrium. They are unknown, but they are the same value, the same numerical value at equilibrium. So I will fill in 1.4 for the concentration of HI. I have that the Kc, or the value of the equilibrium constant, is 49.7, and now I will do the algebra. So 1.40 squared divided by 49.7 is equal to the product of concentration of hydrogen times concentration of iodine at equilibrium. So 1.4 squared divided by 49.7 is equal to this numerical value, which I am choosing not to round off since this is not my final answer. All I have to do now is take the square root of this value. And when I take the square root, that will give me the concentration of hydrogen as well as the concentration of iodine at equilibrium. So the square root of that number gives me 0.199. And so now I will fill in the final row of my rice table with concentrations of 0.199 molar for both hydrogen and iodine. So using my rice table and also a little bit of algebra with respect to the equilibrium constant expression, we have now officially answered part A, calculate the concentration of hydrogen present in the reaction vessel when the system had reached equilibrium, and that is 0.199 molar. So now let's move on to part B of question 6. In part B, it says to calculate the number of moles of hydrogen that was initially added to the 4-liter reaction vessel. So we will fill in the rest of the rice table by moving from the bottom to the top. Let's focus on the change row of the rice table. Since the hydrogen iodine was 0 and now it's 1.4, well, that is a change of 1.4. And since 2x is 1.4, then that means that x is half of that value, which is 0.7. So I can fill in the change row of the rice table as minus 0.7, minus 0.7, and plus 1.4. And these changes are in terms of molarity. These changes are not in terms of moles, they are in terms of molarity. So what is 0.199 plus 0.7? Well, 0.199 plus 0.7 will give me the initial concentration, and that would be 0.899 moles per liter for both the hydrogen and the iodine. Now, you might think that that is the final answer to part B, but this is a molarity. This is not the number of moles. And also, this is not a 1-liter vessel. This is actually a 4-liter reaction vessel. So because it's a 4-liter reaction vessel, we take 4 liters. Remember that molarity is moles per liter. So I will use 0.899 moles per liter as a conversion factor. So 4 times 0.899, this will give me the answer to part B of question 6. So when I do that math, I get 3.60 moles of hydrogen were added initially to the 4-liter reaction vessel. So that's my answer to part B. So that rice table was very helpful, especially in answering part B of question 6. Now, let's take a look at question 7. In question 7, we are given a balanced chemical equation. We are also given the equilibrium constant Kp for this reaction at 500 Kelvin, and it says that a sample of substance AX was added to a previously evacuated reaction vessel. The initial partial pressure of AX was equal to 4.18 atmospheres, and the reaction was allowed to proceed at 500 Kelvin, according to this balanced equation shown above, until the system reached equilibrium. Calculate the partial pressures of all 3 gases in the reaction vessel at equilibrium. So this is a great example of when I think it's a good strategy to go ahead and create a so-called rice table. So that's what I will do. I'm going to fill in my initial row of my rice table with the partial pressure, 4.18 atmospheres. That's the initial partial pressure of substance AX. And since substance AX was the only substance added to the reaction vessel initially, I can fill in 0 for the partial pressures of the products A2 and X2 before any reaction occurs. Now, in terms of the change row of this rice table, since my coefficients are 2, 1, and 1, and the magnitude of the changes for the reactants and the product should be proportional to the coefficients in the balanced chemical equation, I would expect 2x, so in this case it will be minus 2x for the change in substance AX, and then plus x and plus x for the changes for the products A2 and X2. So now let's go ahead and fill in the final row of this rice table in terms of x. So the partial pressure of substance AX at equilibrium is 4.18 minus 2x. And the partial pressures of each of the gases that are the products, so A2 and X2, are simply listed as x and x. The next thing that I will do is I will write the equilibrium constant expression for this reaction. Now, because it's a Kp as opposed to a Kc, I will not use hard brackets, which indicate concentrations. I will use capital P, which indicates partial pressure. So the equilibrium constant expression for this reaction is written as follows. Partial pressure of substance A2 times partial pressure of substance X2 divided by the partial pressure of substance AX squared. Now, the next thing that I will do is create an algebraic equation based on this equilibrium constant expression. So I will take the number 81, which is the magnitude of the equilibrium constant Kp, and I will take each of the quantities that are listed in the final row of my rice table, and I will create this algebraic equation so we can solve for x. So what goes in the numerator would be x times x. What goes in the denominator would be the quantity 4.18 minus 2x, which is squared, and I set that equal to the value of Kp, which is 81. Now, at this point, you might think that this algebra seems too complicated and might involve some sort of quadratic equation or mathematical solver. So here is a tip. You can recognize this if you look closely at the numerator and the denominator. You will recognize that both the numerator and the denominator are perfect squares. So because this expression is a perfect square, then we can greatly simplify our algebra by taking the square root of both sides of the equation. So what is the square root of x squared? Well, that will just be x. And what is the square root of the quantity 4.18 minus 2x squared? Well, that will just be 4.18 minus 2x. And what is the square root of 81? Well, that will be 9. So now I have greatly simplified this equation by taking the square root of both sides. So now I have x divided by the quantity 4.18 minus 2x is equal to 9. The next thing that I will do is I will multiply both sides of the equation by the expression 4.18 minus 2x. Now I will take the number 9 and multiply by 4.18. And I will also take the number 9 and multiply by negative 2x. So when I do that, I get 37.62 minus 18x. The next thing that I will do is I will add 18x to both sides of this equation. So I get 19x is equal to 37.62, and then x is equal to the number 37.62 divided by 19. And when I do that math, I get that x is equal to 1.98. So I will take the 1.98 and I will fill it in terms of x in the change row of the rice table. So there's plus 1.98 for the increase in the partial pressure for each of the products, and then 2 times 1.98 is equal to 3.96. So the change is minus 2x, and that becomes minus 3.96. Now I will do the change in partial pressure from top to bottom. So 4.18 minus 3.96 is equal to 0.22 atmospheres. And then for the other ones, it would simply be 0 plus 1.98. So these numbers that you see in the bottom row of our rice table are the partial pressures of all 3 gases in the reaction vessel at equilibrium. Sometimes our rice table is in terms of moles. Sometimes our rice table is in terms of molarity. And sometimes our rice table is in terms of partial pressures. But since the partial pressures are proportional to the number of moles based on the properties of gases, then you can use a rice table with either moles, molarity, or partial pressures to fill in the quantities in your rice table. So that rice table was a very helpful strategy in answering question 7. Now let's take a look at question 8. So what we will see with both question 8 and question 9 is that they will involve a comparison of the reaction quotient Q with the value of the equilibrium constant K. So in question 8, we are given a balanced chemical equation. We are also given that the equilibrium constant, Kc, for this reaction is 4.0 times 10 to the negative 2. It says a mixture of substance R, substance Z, and substance R2Z3 is placed in a previously evacuated rigid container and allowed to reach equilibrium at a constant temperature as shown above. Which of the following sets of initial concentrations would lead to the formation of additional product R2Z3 as the system moves toward equilibrium? So this is definitely a Q versus K kind of strategy. So that's why I'm writing the equilibrium constant expression in terms of Q, because I do not know until I actually calculate Q and compare it with K whether there will be a net conversion from left to right or whether there will be a net conversion from right to left. So my Q expression looks identical to the K expression. It's going to be products over reactants. I'm using hard brackets because this is a Kc in terms of concentration. This is not a Kp in terms of partial pressure. So the concentration of the product R2Z3 divided by the product of the following, the concentration of R squared times the concentration of Z cubed, again using the coefficients as exponents. So let's start with choice A and then move all the way to choice D, calculating the value of the reaction quotient Q, and then we'll move from there. So starting with choice A, I will place the appropriate values into the reaction quotient. So it's going to be 1.5 divided by the product of 0.5 squared times 2.5 cubed. So when I do that math, I get 0.384. At this point, I'm just going to write it down, and then I will move on to choices B, C, and D, doing a similar type of calculation. So in choice B, the math is the following. 3 divided by the product of 0.5 squared times 3.5 cubed. So when I do that math, I get a value of 0.280 for my reaction quotient. And now moving on to choice C, the math involved is 3 divided by the product of 1.5 squared times 2.5 cubed. So when I do that math, I get that the value of the reaction quotient is 0.0853. And then now finally moving on to choice D, when I set up the math for the reaction quotient, it's 1.5 divided by the product of 1.5 squared times 3.5 cubed. And so when I do that math, I get that the value of the reaction quotient is 0.0155. Well, the next step in the process is to compare the value of Q with the value of K. We see that the value of the equilibrium constant K is 4.0 times 10 to the negative 2, and that can also be written as 0.040. And we have to determine which of the following sets of initial concentrations would lead to the formation of additional product R2Z3 as the system moves toward equilibrium. So what should the value of Q be relative to the value of K if I would like there to be a net conversion from reactants to products or from left to right? Well, as we can see from topic 7.7, when the value of Q is less than the value of K, the reaction will proceed with a net consumption of reactants and generation of products. In other words, a net conversion from left to right. And so looking at the four choices, since the value of K can be written as 0.040, then we can see that choice D is the only correct answer. Why? Because choice D represents a set of concentrations in which the value of Q is less than the value of K. And that would lead to the formation of additional product R2Z3. So the reason why choices A, B, and C can all be eliminated is because the value of Q for choices A, B, and C is actually greater, not less than, but greater than the value of K. Now, there is a similar comparison of Q and K in question 9. Let's go ahead and move on to question 9. So in question 9, we are given a balanced chemical equation. We see that the value of the equilibrium constant, Kp, for this reaction is equal to 58. And question 9 says the following. A vessel initially contains NO2 gas at a partial pressure of 0.10 atmospheres and N2O4 gas at a partial pressure of 2 atmospheres at a temperature of 273 Kelvin. Which of the following occurs as the system approaches equilibrium at 273 Kelvin? So first we will calculate the value of Q, and then we will compare the value of Q with the value of the equilibrium constant K. Remember that this is a Kp, so I will write this in terms of partial pressures. So products over reactants, the reaction quotient Q looks like this. Partial pressure of N2O4 in the numerator, partial pressure of NO2 squared in the denominator, and that's because of the coefficient of 2 from the balanced equation. Let's go ahead and plug in our values from this question. So in the denominator, that will be the partial pressure of NO2, which is 0.10 atmospheres. In the numerator, it will be the partial pressure of N2O4, which is 2 atmospheres. I pick up my calculator and I will do 2 divided by 0.1 squared. And so when I do that math, I get 200. Now, how does 200 for the value of Q compare with the value of K, which is 58? So unlike the previous problem, question 8, where Q was less than K, here in question 9, we can see that the value of Q is actually greater than the value of K. So we have to ask ourselves, what happens to the system when Q is greater than K? So now there will be a net consumption of products and generation of reactants. So when the value of Q is greater than the value of K, there will be a net conversion from products to reactants or from right to left. So if we're going from right to left when Q is greater than K, then that means that the partial pressure of N2O4 will decrease. So the correct answer to question 9 is choice B. Because Q is greater than K, and there will be a net conversion from products to reactants or from right to left, the partial pressure of N2O4 decreases. All right, well, hopefully those Q versus K comparisons in questions 8 and 9 in this packet, if that all makes sense to you, let's go ahead and move on to the review for topic 7.8, representations of equilibrium. This will involve particle diagrams. So the essential knowledge statement from the AP Chemistry course and exam description is that particulate representations can be used to describe the relative numbers of reactant and product particles present prior to and at equilibrium, as well as the value of the equilibrium constant. Now let's move on to the practice for topic 7.8. This is question 10. So as you will see, the strategy for answering both question 10 and question 11 in this packet will be to examine the details of the particulate diagrams, to count the number of particles of each substance, and then take those numbers and substitute them into the equilibrium constant expression or the reaction quotient expression. So here are the details of question 10. It says the substance Dg2 undergoes a decomposition reaction to produce substances D2 and G2 at 600 Kelvin according to the equation above. Which of the following particulate diagrams is the best representation of the reaction mixture after equilibrium has been achieved at 600 Kelvin? And then it makes a note that we can assume that each molecule in the diagram represents a partial pressure of 1 atmosphere for that substance. So our equilibrium constant expression will be products over reactants, and it will be a Kp, so not concentration, so not hard brackets, but rather capital P for partial pressure. So it looks like the following. The partial pressure of substance D2 times the partial pressure of substance G2 squared, and then divided by the partial pressure of substance Dg2, which is also squared. Again, because the coefficients of 2 are listed next to those substances in the balanced equation. Now, if we can get a numerical value of 4.5 when we do the math, then that will be the correct answer to question 10. Let's go ahead and begin with the diagram for choice A. The first thing that I notice is that I see 2 particles of substance D2. And so that means that the partial pressure of D2 is 2 atmospheres. So I will put the number 2 into my expression. Moving on to the substance G2, I see 2 particles of substance G2, so it also has a partial pressure of 2 atmospheres. I substitute the 2 into that expression. And then finally, substance Dg2, I see 3 particles of substance Dg2 that would correspond to a partial pressure of 3 atmospheres. So that's where the 3 goes in the denominator of my expression. Now, when I do the math of 2 times 2 squared divided by 3 squared, if I get 4.5 for my answer on my calculator, then choice A is the correct answer. But unfortunately, I get 0.89. So what I can say at this point is we can go ahead and eliminate choice A. Moving on to choice B, similar strategy. The first thing that I notice is that there are 3 particles of substance D2, so that would correspond to a partial pressure of 3 atmospheres. So I put a 3 into my expression. Then I see 2 particles of substance G2, that's a partial pressure of 2 atmospheres for G2, that goes in the numerator. And then I see 3 particles of substance Dg2, so a partial pressure of 3 atmospheres, that goes into the denominator of my expression. Again, if I pick up my calculator and I do 3 times 2 squared divided by 3 squared, if I get 4.5, then choice B is the correct answer. But when I do that math, I get 1.33, so again, we can eliminate choice B. Let's move on to choice C. I see 2 particles of substance D2. That's a partial pressure of 2 atmospheres for substance D2. I see 3 particles of substance G2. That's a partial pressure of 3 atmospheres for substance G2. So those values go into the numerator. And then I see 3 particles of substance DG2. That's a partial pressure of 3 atmospheres, and that goes into the denominator of the expression. Well, when I do that math of 2 times 3 squared divided by 3 squared, I get 2, which means that not only can I eliminate choice C, but I now know by process of elimination that choice D will be the correct answer. Let's go ahead and verify that the numbers will work out to give us 4.5. So 2 particles of substance D2, partial pressure of 2 atmospheres. 3 particles of substance G2, partial pressure of 3 atmospheres. So that goes in the numerator of my expression. And then 2 particles of substance DG2, partial pressure of 2 atmospheres. That goes into the denominator. So 2 times 3 squared divided by 2 squared definitely gives me a numerical value of 4.5, confirming that choice D is the correct answer to question 10. So we're going to do a similar type of counting particles and substituting the values into the expression in question 11. So now let's go ahead and take a look at question 11. Now, what you will notice in question 11, based on the 4 answer choices listed, that this will be a Q versus K comparison. So the details of question 11 are the following. Samples of substances X2 and X3 are added to a previously evacuated container and allowed to react at a constant temperature of 400 Kelvin according to the equation shown above. The following particle diagram is a representation that shows the relative number of molecules of each substance present in the reaction mixture at a certain time. Notice that this is not at equilibrium, it is simply at a moment during the experiment. And again, it says, like we saw in question 10, assume that each molecule represents a partial pressure of 1 atmosphere for that substance. So I will write the expression for Q as follows. The partial pressure of substance X3 squared, because it has a coefficient of 2. Again, it's products over reactants. And then the denominator, it's going to be the partial pressure of substance X2 cubed, because it has a coefficient of 3. So now I will count the number of particles of substance X3. The number of particles of substance X3 are right there in the diagram. So that's only 2 particles. So that will be a partial pressure of 2 atmospheres. I will place a 2 in the numerator of our expression. Now, when I can look at the number of particles of substance X2, I can see that there are 4 particles of substance X2. That would give me a partial pressure of 4 atmospheres, and I will put that in the denominator. Now, when I pick up my calculator, I'm not expecting to get 16. I'm just going to get a number. And whatever that number is, I will compare the value of Q with the value of K, which happens to be 16. So when I do 2 squared divided by the quantity 4 cubed, this is what I get. 0.0625. And when I compare that to Kp, which is 16, then this will help me determine the answer to the question. Which of the following best predicts what will occur as the system approaches equilibrium at 400 Kelvin? So we have a situation in which Q is less than K. Now, when Q is less than K, what happens to the system? Remember, in topic 7.7, when Q is less than K, there will be a net conversion from left to right, a net consumption of reactants, and generation of products. So I will draw an arrow to indicate that there is a net conversion from reactants to products, or from left to right. And if you look at the 4 answer choices, they all talk about how the amount of substance X3 will change. Well, since substance X3 is a product, and additional products will be formed as this system approaches equilibrium, then the amount of substance X3 will increase. So the correct answer to question 11 is choice B. The amount of substance X3 will increase because Q is less than K. All right, well, hopefully the answers to questions 10 and 11 in terms of particle diagrams make sense. Now we come to the point in the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice for you is that you can review the information in my video for topics 7.1 to 7.5 or my video for topics 7.6 to 7.10 if you need additional practice problems and information. And again, the links to those two videos are in the video description area. My next piece of advice is what I normally say during this point in the lesson. Read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations. Remember that the magnitude of the equilibrium constant K indicates which substances, that is, the reactants or the products, are favored at equilibrium. Now, the value of the equilibrium constant K can be large or small, but note that the value of K will always be positive. So the value of K is never negative. And as you learned in topic 7.5, if the value of K is very large, for example, 1,000 or greater, then the forward reaction from left to right essentially goes to completion. And if the value of K is very small, so for example, 10 to the negative 3 or less, then the reverse reaction from right to left essentially goes to completion. And as I mentioned, setting up a Rice table is a helpful strategy to keep track of the changes that occur in the amounts, moles, concentrations, or partial pressures of the reactants and products as a chemical reaction occurs moving toward a state of equilibrium. Now, what I'd like to show you as a piece of advice is to compare and contrast what you had learned in topic 6.9, Hess's law involving thermochemistry, with what you learned in topic 7.6, properties of the equilibrium constant. So notice that there can be various modifications to a chemical equation. And how will delta H, or the change in enthalpy for a reaction, be affected by this modification? Versus how will the equilibrium constant K be affected by this modification? So let's start with the first modification, which is, what if the equation is reversed? Well, for delta H, the new value of delta H for the reversed equation is equal to the negative of the old value of delta H. In other words, you change the sign of delta H. However, we know that the value of K can never be negative. So when an equation is reversed, the new value of the equilibrium constant K is equal to the reciprocal of the old value of K. Now, what about if each coefficient in the equation is multiplied by n? Well, back in Unit 6, thermochemistry, you learned that when you multiply each of the coefficients by 2 or by 3, then you would multiply the value of delta H by that same value. But for equilibrium constants, the original value of K is now raised to that power n. So again, compare and contrast with what you learned in Unit 6 with what you are learning in Unit 7. And then finally, we saw with Hess's law that when you have two or more equations added together, you simply add the values of H together. But that's not what we are doing with the equilibrium constants. So we don't add them together, we actually multiply them together. So just a good example of compare and contrast with topic 6.9, Hess's law, and topic 7.6, properties of the equilibrium constant. Now, the next thing that I'd like to share is something that I had presented in one of my videos about when you're comparing Q versus K. So if Q is less than K, then the situation is the following. You could consider Q is less than K, you have too many reactants or not enough products. And if Q is less than K and you write it in this fashion, so K is written before Q, K is greater than Q, you can see that the inequality actually kind of points as an arrow to show you in which direction the system will proceed. There's a net conversion of reactants to products or from left to right if Q is less than K. On the other hand, if Q is greater than K, you can consider that we have too many products or not enough reactants. So that would now be a net conversion from right to left. And if you set up the comparison in which Q is greater than K by putting K first, then you can see that the inequality represents the arrow telling you that we are going to proceed from right to left. So Q is less than K, there is a net conversion from left to right. Q is greater than K, there's a net conversion from right to left. All right, my next piece of advice for you is that when solving problems that involve equilibrium and particle diagrams, be sure to do the following. Count the number of particles of each substance correctly. Write the correct expression for the reaction quotient Q or the equilibrium constant K. When substituting the values from the particle diagram into the expression for Q or K, be careful to avoid errors with arithmetic or algebraic manipulations. And pay attention to the instructions about what each particle in the diagram represents. Okay, so now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 7.9 and 7.10. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.